Alrighty, howdy folks. Some of you may not know this practice that I have. Uh, I have this habit of saying howdy, as if I'm some kind of a country boy from Tennessee. I'm not a country boy from Tennessee, but I just like to say howdy. There's a big long story behind it, but I'm not gonna bore you with it. Maybe when we meet in class, I'll talk about it. So, without much further ado, let's get on with differential equations. Oh boy, DiffE is a very important course. Uh, do I go around saying that in every class? Yeah, probably I do. Hey, calculus 2, man, this is a very, very important course. But the thing is, DiffE is important because this is exactly what all your engineering professors are waiting for you to take. They want to talk to you about, hey, you we try to model this one, and so all you need to do is solve this second order differential equation. Oh, wait a minute. You guys don't know how to solve differential equations yet, right? Scratch that idea. So once you take this class, there are so many avenues that will open up. Okay, folks? All right, so let's move on. Uh, oh, I should have connected a mouse, but oh, let's see. Uh, I'll do click click. I hmm, okay. Uh, then what's a differential equation? I'm going to give you a formal definition and all that. But if you were to take a guess, what do you think a differential equation is? Here is the idea, folks. Have you ever seen an equation? Forget about the differential equation. Just do you know what an equation is? Have you seen one? Of course you have, right? Mm, is x plus 2 an equation? No, it's not. But if I say x plus 2 is equal to 3, is that an equation? Yeah, man, that's an equation, right? So what is an equation? An equation is something like you have two sides of an equal sign, right? You have an expression equals another expression. Let me put it that way. That's a better way of saying it. An expression equals another expression is an equation. In that example that I gave, x plus 2 equals 3, you have an expression x plus 2 on the left-hand side of the equal sign and 3 on the right-hand side. Okay, now, what kind of an equation is that? I'll say that's an algebraic equation because you got things like x plus 2 and 3, and that's kind of algebraic equation. But then we also looked at equations like sine x is equal to 1 half, or I could say sine x plus 1 half is equal to 1, right? So can you solve an equation like that? Is that an equation to begin with? Sine x plus 1 half equals 1. Yep. So what kind of an equation is that? That's a trigonometric equation. So algebraic equation has algebraic terms. Trigonometric equation has trigonometric terms. And so a differential equation should have what kind of terms? Derivative terms. As simple as that. So it's going to be an equation and it has derivatives in it, or even differentials. What is a differential and all that? I'll explain to you in just a little bit. But a differential equation is just an equation with differentials in it. But with that, let's move on to a more formal definition. A differential equation is an equation containing the derivatives or differentials of one or more dependent variables with respect to one or more independent variables. Have you ever bumped into anything like this? Dependent, independent, like that? Yeah, excuse me. Um, yeah, you have seen something like that. Okay. If I said y equals f of x, what are x and y? Would you agree x and y are variables there? What kind of a variable is x? It's an independent variable. Why do we call it an independent variable? Because x can take on whatever value in the domain. So you are free to choose some value for x. But y is a dependent variable because its value depends on the value of x, right? So when we say y equals f of x or y equals x squared plus 2, for instance, then x is an independent variable and y is a dependent variable. Well, sometimes that kind of a difference is a bit nebulous. It's not so crystal clear. Now, if you asked me, why do you say that, man? I can always say y equals x squared plus 2. So x squared is equal to y minus 2. And so x equals, plus or minus square root of y minus 2. Suppose I'm interested only in positive values. I can say x equals square root of y minus 2. Then haven't I changed x to be the dependent variable and y as the independent variable? Yep, you did. Right? So in what I'm trying to simply say is, if we were to express this as y equals some f of x, in that case, x is the independent variable and y is the dependent variable. Okay, so what is a differential? It's an equation containing the derivatives or differentials of one or more dependent variables. Do you know of a situation where there is one dependent variable? Yeah, y equals f of x. There, that's one dependent variable y. Um, or more? What in the world is that? Right? Could you have more than one dependent variable? That's an interesting question, right? Now, with respect to one or more independent variables, wait a minute, are you telling me that there could be more than one independent variable as well? That's really, really interesting now, right? Let's go with one independent variable. Can you think of one? Y equals f of x. Is that one independent variable and one dependent variable? Yeah. Okay. Can you think of a situation where you have two independent variables? One dependent, two independent variables. Can you think of a scenario like that? Those of you who took Calculus 3 will say, piece of cake, man. And those who have not probably will struggle just a tad bit to answer that question. But that's okay. Don't worry too much about it. Okay? So what is this then? Well, you could have z equals f of x comma y. You could have z equals f of x comma y. When you do, then I'm writing with the stylus. I don't know how to erase with this one. Okay, we'll cross the bridge when we get there. Is that the American expression? All right, z equals f of xy. In that case, we have x and y to be independent variables and z is the dependent variable. Okay. Fine. Now let's go back and address that question that I asked you just a while ago. Can you think of more than one dependent variable? Two. Let's say two dependent variables, but only one independent variable. Check this out. What is that? Two dependent variables and one independent variable. Could you have a situation like this? X equals f of t, y equals g of t. Y equals g of t. Yep. Ah, is that a case where you have one independent variable t, but two dependent variables x and y? That's the idea. Well, if we go with that, could we think of a situation where you have two independent and two dependent variables? Yep, we can. As in, u equals f of x comma y, and v is g of x comma y. There we go. Right? So all those possibilities exist. And now, what is this saying? Is an equation containing the derivatives or differentials of one or more dependent variables with respect to one or more independent variables. Can you think of a derivative with one dependent variable and one independent variable? A derivative, dy dx. So, if we have a dy dx is equal to x, let's say, is that a differential equation? Yep, we have a derivative. It is an equation to begin with, and it's a differential equation because it's got derivatives in it, right? And here it happens to be one independent variable and one dependent variable. That's a differential equation. Okay. What about a differential equation where you have, which one is better to go with? Let's go with one independent variable and two dependent variables. Can we think of a differential equation in that scenario? Let me repeat that. One independent variable, which refers to this scenario, and two dependent variables. X and y are both dependent variables. Can we come up with a differential equation of that kind? Yes. Dx dt plus dy dt is equal to sine t. That's a differential equation with one independent variable and two dependent variables. Cool? All right. Can you now think of the other scenario where we have z is a function of xy, that is one dependent variable but two independent variables, right? Well, if you have not taken calculus 3, you might not know this, but here is a scenario where you have to use what are called partial derivatives. You write like this. Instead of a d, you write this funny looking d, and you read this as partial z with respect to x plus partial z with respect to y is equal to xy. Something like that. Now that is a differential equation involving partial derivatives. What exactly is a partial derivative? I'll give you, when the time comes, I'll explain to you. Right? Don't worry too much about that. What does this mean? Don't worry. And of course, we are not going to solve partial differential equations. We are not going to solve differential equations that contain partial derivatives. We are going to deal with only what are called ordinary differential equations. All the derivatives are just ordinary derivatives. Cool. All right. So this is what they're talking about with the definition. All right, let me erase all this. That would be so easy. I thought I could just right click and it would help me. Green, that's green. Sure, hide ink markup. Huh, as simple as that, huh? Isn't that cool? I learned something today. Okay, let's move on. A differential equation with one dependent and one independent variable. Okay? That is d square y dx square plus y equals 2x. Do you agree that's that kind of a differential equation? Yep. Y is the dependent variable, x is the independent variable. A differential equation with differentials. Do you remember what have you ever come across that term differential? You did. Where? In Cal 2 especially, of course even in Cal 1, but Cal 2, you needed this quite a bit, where when you use the substitution rule, right? For example, you say u equals x squared. I'm going to substitute u equals x squared, man. Okay, when you substitute u equals x squared, what do you say immediately? Then you say du equals 2x dx, right? What do you think that du is? It is a differential. Okay, and dx, that is a differential. You have come across a differential before. Now, check this out. We could have a differential equation with differentials like this. X squared dx, dx is the differential, plus x, the quantity x plus 1 times the differential dy equals sine x. Cool? What are differentials dx and dy? As promised, I'll explain to you what these are. Suppose I have a graph of some y equals f of x, okay? And there are 2 points, as you can see. There are 2 points there. Now, the x distance between them, or the x coordinate of the left point is x, and the x coordinate of the right side point is x plus delta x. Right? So what's the distance between them? Like, what is this distance I showed with a double arrow like that? Yeah, simple. Man, x plus delta x minus x, which is delta x. Right? So here, what I'm trying to say is, when you go from one point on the left to another point on the right in the graph, the change in the x value is equal to delta x. Did you get that? The change in the x value when you go from the point on the left to the point on the right is what is called delta x. Change in x. Cool. The moment I say something like that, and I ask you this question, right? What question? Well, something popped up on the screen, right? What is that? That vertical thing. This guy. I'm asking, what do you think we should call that? Uh, well, does that indicate a change in the y direction? Just as delta x is a change in the x direction as you went from one point to the other. Here, it's the change in y as you go from the one point to the other. Now, what should we call that? Logic dictates, and maybe we should call it delta y. Yep, you're right. So delta y is the change in y, right? Yeah, man, that's fine. You've got delta x and delta y. but I thought we were going to talk about differentials dx and dy. What's that got to do with all of this? Check this out. Now, dx and delta x are exactly the same. There is no difference. Oh, okay. So that means dy and delta y are the same. No. That's where the difference comes. Okay. So dx and delta x are the same. But what is this dy? For that, this is what we need to do. We need to draw a tangent at that x and f of x to the graph and measure the difference, measure the y difference along the tangent. But that's, what do you mean? Is that's delta y? No, it's not. But dy and delta y are completely different, even though dx and delta x are exactly the same. Yeah, that's true. You're right. But then you should understand, I exaggerated the figure, right? Dx and delta x, if we were to make them very, very small, then you can see that the change between delta y, the difference between delta y and dy wouldn't be quite as much as what you see in this picture, right? So because of that, don't worry too much about the fact that at least in this case, the figure shows a drastic difference between delta y and dy. That won't always be the case, especially when you take dx or delta x to be very small. So anyways, what is dy? The differential dy? It's the difference, it's the change in the y along the tangent drawn at x. As simple as that. That's what a differential is. Differential dy is. Cool? Alright, let's move on. Now, a differential equation with two dependent and one independent variables. Dx dt plus t squared dy dt equals cosine t. Clearly see that t is the independent variable, which is 1 in number, and x and y are the two dependent variables. So there we go. Now, a differential equation with one dependent and two independent variables. Ooh, that's an interesting one. For this, we need to recall a multivariable function as seen in calculus 3. This is what I was talking about. Z equals f of xy. And so, now we will say something like second partial of z with respect to x plus second partial of z with respect to y equals sine of xy. That's how you read that, folks. You don't say d square z dx square, even though some people, in fact, they look at the partial, but they just say d square z dx square. Or in India, in fact, I have seen some other people from other countries too. They read that as dou square z, dou x square, instead of d square z dx square. But in America, at least my advisor always called it a second partial z with respect to x, and that's what I always do. Okay, second partial z with respect to x plus second partial z with respect to y equals sine of xy. That's a differential equation with one dependent and two independent variables. Okay, classification of differential equations. Incredibly important to classify. Why? Why? What's the big deal? Oh man, it is such a big deal because when you try to apprehend a very complicated thing or a complicated in the sense there are way too many numbers up there, way too many of something. For example, life forms on the earth, right? There are many, many, many life forms. And now we as intelligent humans, we want to get a grasp of all of the complexity of life forms. So what do? We say, let's classify. Okay, classify what? On the topmost tier, we have life. Cool. How do we split this life into? Oh, let's split this into two subcategories called plant life and animal life. Right? Why do we do that? Because we kind of notice some marked differences between plant life and animal life. Mm, Something like a quarrel may give us a problem. Is it plant or animal? Uh, I wanted to say, I was tempted to say, uh, animal life moves, whereas plant life stays in one place. Eh, Not so. There may be some exceptions to it. So anyway, whatever it is, we've decided to classify life forms as plant life and animal life. And once again, inside the animal life and inside the plant life, we decided to classify things based on genus, and whole uh, species. Oh, for a second, I forgot to go to genus and species, right? When we say Homo sapiens, the Homo part is the genus, and sapiens is the species part. Hibiscus cannabinus, uh, again, genus and species. And a wonderful example, so far as I'm concerned, is elements, classifying elements, especially the work of Mendeleev, and of course other people also did it, but Mendeleev did the best thing, classifying elements based on some common properties, right? He said, uh, all right. So what did Mendeleev do? He said hydrogen, lithium, sodium, potassium, radium, cesium, francium. Right? He put all of these things in one column. Then he went all the way to the right and he said the noble gases: helium, neon, argon, krypton, xenon, radon, what else? Beryllium, magnesium, calcium, strontium, barium, radium. Right? He did uh, he did classification like that. And here is the best part so far as I'm concerned. That dude was so confident about his scheme. He said, well, right now, folks, there's a blank here. And some other place he had just blanks. What goes there, Mendeleev? Uh, right now, there is nothing that goes in there. But if you guys just look around, you are guaranteed to find an element that fits there. What a confident guy. And sure enough, they did find all those elements to fit in those places. See that? That's the beauty of classifying, folks. All right. So let's try to um, let's try to do that with differential equations. Types. There are two types. ordinary differential equations and partial differential equations. Ordinary contain ordinary derivatives. Partial differential equations contain partial derivatives. As simple as that, right? And it's called an ODE, and partial differential equation is called PDE, contains partial derivatives. Okay, next examples. Y double prime plus 2y prime plus y equals 0. That's an ordinary differential equation because it has ordinary derivatives, d square by dx square and dy dx and y. And the other one is second partial u with respect to x plus blah blah. That is the partial differential equation. By order. This is getting interesting. By order. Order of a differential equation is the order of the highest derivative in the differential equation. Let's see. The order of a differential equation is the order of the highest derivative in the differential equation. What? I don't have an example? Yeah, I don't. Because I'm going to solve a few problems and show you. Okay? Just be patient, please. And I'll show you with quite a bit of examples, all of those things. By linearity. This is very crucial. This is crucial for many reasons. You got to be able to look at a differential equation and say, hey, is this linear or non-linear? Let's say in a few months or whatever, you're working on some project and you need to solve a differential equation and you have no idea how to solve it. And you go to one of your professors and say, hey, Professor so-and-so, could you please help me with solving this differential equation? And they'll be like, okay, let me try. What kind of a differential equation? And I look at, that's non-linear. Forget it, man. Just non-linear differential equations could potentially be very scary. And also, linear equations tend to have some wonderful properties. And that's why we want to know whether the equation is linear or non-linear. And for the most part, anytime the equation is complicated, it would be a linear one. First order, maybe that's easy. That's not so difficult. But higher order differential equations, they better be linear for us to be able to solve, at least in this course. Okay, so what is this? An nth order linear ODE has this particular form. An nth order linear ODE. Take a good look at that. I know that probably looks a tad complicated, but when you break it down and try to understand, it's really not that complicated. Let's look at just the very first term first. A sub n of x. What do I mean by a sub n of x? It's just some function of x. Would you be happy if I said f of x? It's like that. Okay, and that's multiplied by d to the ny dx to the n. What is that? That's the nth derivative of y with respect to x. For instance, you could have something like d cubed y dx cubed. Okay, and so we have a derivative, some nth order derivative, being multiplied by some function of x. That's what the first term is. In the second term, we have similar concept. We have the n minus 1th derivative instead being multiplied by some other function of x. And so if we proceed, the derivative, nth derivative, n minus 1th, n minus 2nd, n minus 3rd, and so you will get down to the third derivative, d cube y dx cube, d square y dx square, dy dx, and y eventually. So I have not shown you all those middle ones, but the trend continues and you can figure out. So the next two last terms, a1 of x dy dx. Yeah, that's dy dx is the first derivative. being multiplied by some function of x. And y, that's not a derivative, man. Of course it's a derivative. You take the 0th derivative. What? dy dx is the first derivative, right? What is the second derivative d square y dx square? It is the derivative of, you take the derivative 2 times to get, okay, let me put, sorry, let me put it this way. If you start with a y and take the derivative once, you get dy dx, which is the first derivative. Do you agree? Okay, now you take the derivative of the derivative. In other words, you take the derivative 2 times of y. That is what your d square y dx square is. So you can take the derivative of y once or twice or 3 times or so on. But if that is the case, couldn't you take the derivative 0 times? Which means what? Which means don't take the derivative, leave it alone. Right? So y could be thought of as the 0th derivative. Okay, and that is being multiplied by some function of x. We are labeling them a sub n minus 1 and all that because we want to write it in a logical way. First derivative has a coefficient of a1 of x. A1 of x is just some function of x, as simple as that. There's nothing fancy about it. Okay, all right. So this, and on the right hand side we have g of x. Oh, there's a lot more I need to talk about. So notice, in this nth order linear ODE, this is what we have. All the y terms and its derivatives of y, all those terms are on the left hand side. Do you agree? And if you have only x terms, that is on the right hand side. The moment a term has a y in it, y or its derivatives, then that better be on the left hand side of this equal sign. That's one of the things that you must see in a linear equation. Cool. What else do you need to see? Notice that let's go back to the first term, a sub n of x d to the ny dx to the n. In that, the derivative, the nth derivative, is raised to what power? What? Yeah, d to the ny dx to the n is raised to what power? A power of 1. We do not have d to the ny dx to the n, the quantity cubed, or quantity raised to 4, or square root of d to the ny dx to the n. We cannot have that. If you want the equation to be linear, the derivative terms must be raised to a power of 1. Every derivative term. That's not only true of the nth derivative, but the n minus 1, the n minus second, the third, second, first, and even y, the 0th derivative, must be raised to a power of 1. That's the first requirement. In addition, every derivative must be multiplied by purely a function of x. Can you remember that? Every derivative must be multiplied by a function of x alone. Can you think of some function of x? Is x squared plus 3 a function of x? Yep. So could the coefficient of d to the ny dx to the n be x squared plus 3? Yeah, it could be, because x squared plus 3 is just purely a function of x. Could the coefficient of d to the ny dx to the n be something like x squared plus y squared? No, right? Because when you say x squared plus y squared, that is a function of both x and y, which is a known. The coefficient of a derivative must be purely a function of x. That's the idea, right? If you can remember those things, you are in a good shape so far as figuring out is this equation linear or non-linear, and also we'll do order. I'm going to solve quite a few examples, so don't worry about I don't know, man, this stuff went way over my head. No, once you see a few examples, this will become clear. But before I actually show you more examples, let's recall exactly what properties should this nth order linear equation should have. All the y terms, including its derivatives, must be on the left hand side. Purely x terms on the right hand side. That's one requirement. Every derivative, including the zeroth derivative y, must be raised to a power of 1. No square roots allowed for those derivative terms. No squares, cubes, nothing other than 1 as a power. Cool. That's the second requirement. Third requirement. Every derivative must be multiplied by purely a function of x. If a differential equation satisfies all those things, it's a linear differential equation. Cool? Now we are ready to solve problems. In exercise 1.1, the first problem says, is the following differential equation linear or non-linear? What is its order? 1 minus x y double prime minus 4xy prime plus 5y equals cosine x. Let's see. Is that a differential equation to begin with? Yeah, man. Why? Because it's got derivatives. How many dependent variables and how many independent variables? One independent x and one dependent y. Yep. So that is a differential equation for sure. Is it ordinary differential equation or partial differential equation? We see only ordinary derivatives, so must be an ODE, right? Then, what else? Now let's focus. What order is this? How do we determine the order of a differential equation? We look for the highest derivative, the order of the highest derivative. What all derivatives we have? We have a zeroth derivative y, first derivative y prime, and a second derivative y double prime. Okay, which one is the highest derivative? The second, y double prime. So we have to say this is a second order differential equation. Cool? All right. Now let's focus on the more important linear part of it. Is this a linear differential equation? Do we have all the y terms on the left-hand side? Yep. Do we have all pure x terms on the right-hand side? Yep, we do. Good. Now let's look at it. Are all the derivatives raised to a power of 1? We have y double prime. That's it. We don't have a y double prime square or cube or anything like that. So y prime, same idea. Y raised to a power of 1. Cool. So far as the derivatives are concerned, they are all raised to a power of 1. That's good. Now final thing, coefficients. Is the coefficient of y double prime purely a function of x? What is the coefficient of y double prime? 1 minus x. Is that purely a function of x? Yep, it is. What's the coefficient of y prime? Be careful. Do not say 4x. Well, the coefficient is negative 4x. Cool. Is negative 4x purely a function of x? Yes, it is. And now, coefficient of y. Uh-oh. 5. Is 5 purely a function of x? No, man, it's just a constant. Could you not have constant functions? So you're telling me that you would have no problem saying, if I say, hey, y equals 3x plus 4, is 3x plus 4 a function of x? Yeah, of course, like y equals 3x plus 4, you said, why that's like y equals f of x. What is f of x? Oh, 3x plus 4. Okay. Can I have y equals 5? Why not? I could. What is that? When you draw the graph of y equals 5, it's a horizontal line drawn at a y value of 5. So every constant function, every constant is a constant function of x. So constants are okay. The 5 is a function of x. Cool? Alright. So this one satisfies all the requirements of linearity. We can confidently say this is a second order linear equation. Cool? Next. What about this guy? Are all the y terms on the left-hand side and x terms, purely x terms on the right-hand side? Yep, good. Now let's begin to examine. The right side is 0. Is that a problem? Hey, in the previous one I forgot to show. Oops. The right-hand side being cosine x, a function of x. But was that okay? Yep, that was okay. That's what it's supposed to be, a function of x on the right-hand side. Now in this problem, is the function on the right-hand side purely a function of x? Yeah, 0. It's a constant function of x. That's cool. Let's look at x d cube y dx cube. Is every derivative raised to a power of 1? D cube y dx cube is raised to a power of 1. The 0th derivative y is raised to a power of 1. But Houston, we got a problem. dy dx has been raised to some stupid power of 4. That makes it nonlinear. Cool. What's the order of this one? What's the order? Order is the order of the highest derivative in the differential equation. What is the highest derivative in this one? Is the order 3 or 4? Why do you say 4, man? Oh, let's see. Is dy dx the quantity raised to 4? Isn't that the same as d to the 4y dx to the 4? So this is the 4th order, isn't that right? Ladies and gentlemen, please indulge me. Those who have had some courses from me before, they know this. But if you never took a class from me, this will be mildly entertaining. Okay. Indulge me. What does this symbol mean? Equals. Cool. Right. What does this symbol mean? Does not equal or not equal to. Right? Cool. Now, what does this symbol mean? You have to say that in Southern accent. That's the only right way of doing it. You gotta say in a Southern accent and say that's big time not equal to. Alright? That's because certain things, it's not enough to say, hey, that's not equal to that, man. You gotta go, whoa, stop, man. That's big time not equal to. Now, guess what? Let me tell you something, folks. Dy dx, the quantity raised to 4, that's big time not equal to d to the 4y d to the dx to the 4. Y'all get it? I know, I'm trying to be funny, but I sincerely hope you get that one, right? No. So this is not a fourth order differential equation. It is in fact a third order differential equation. Okay, folks? All right. And it is nonlinear because the dy dx has been raised to a power of 4. A derivative must be raised to a power of 1. That's the requirement. All right. Sixth problem. D square y dx squared plus 9y equals sine y. I'll let you tell me. Is anything wrong with d square y dx squared? Oh, is it raised to a power of 1? Yep, it is. What's its coefficient? It doesn't have any coefficient, man. No, man, it does. Right? 1. Is 1 a constant? Is 1 a function of x? Yeah, constant function of x. There's nothing wrong with the term d square y dx squared. Cool. Plus 9y. Is everything fine and dandy with that one? Yep. Hey, but what happened to the dy dx, man? Well, maybe the coefficient of dy dx is 0, so that's why it disappeared. This differential equation could very well have been written as d square y dx squared plus 0 dy dx plus 9y. But what's the point in writing 0 dy dx when the product is 0? Right? Okay. So nothing wrong with the left-hand side. Oh, right-hand side is sine of y. We really should have written this where we had that right side term on the left hand side because it's got a y in it. It has no business staying on the right hand side. We should have pulled it to the left hand side. Okay, let's assume I did. I pulled it to the left hand side. Is sine y okay? No, that's not okay. Y must have a coefficient as a function of x. Sine y is you cannot have sine y, cosine y, tangent y, e to the y, y square, y cube, all those things are a no-no. This is nonlinear because sine y, when brought onto the left-hand side, is a nonlinear term. What order is it? That's a simple one, second order. Cool. How about this guy? Dy dx is equal to 1 plus square root of 1 plus the quantity d square y dx square. Oh man. Oh, Dr. Sam. I know you're trying to trick us now. Yeah, maybe. Hey, wait a minute. I just got an idea. The right hand side, isn't that simply 1 plus d square y dx square? And when you take the square root, man, what? Isn't the right hand side, this is what I'm asking, doesn't the right hand side simplify to 1 plus, means square root of 1 is 1, square root of d square y dx square is just d square y dx square, the square disappears. So isn't that just 1 plus d square y dx square? In other words, this is what I'm asking. Isn't square root of a square plus b square, isn't that equal to a plus b? Right? Square root of a square plus b square, isn't that equal to a plus b? Dang, how come this equal sign became this long? because I'm fixing to make it a big time not equal to. No, that's not equal to a plus b, right? Please do not ever, ever, ever make that mistake. Nope, that is not true. Square root of a squared plus b squared not equal to a plus b. Cannot simplify that. So, what's the order? D square y dx square is the highest order derivative, so second order derivative, and it's highly nonlinear. You cannot have a square root of d square y dx square being raised to a power of 2. Second order non. Cool? Hide that again. Okay. Check this out. I'll ask you quite likely in a quiz, first quiz, which will cover this one, and the first test. I will probably ask you a trick question like this. I don't like trick questions, but for 1 point, one measly point out of 20, I do want to test this. Okay? So let me warn you. This is a trick question. Okay. Order. Second order. D square y dx square. Yep, that's done. Linear or non-linear? D square y dx square. Anything wrong with that? Nope. Cool. Dy dx. No, cool. Sine square y. No. You cannot have sine y, sine square y. Forget it. That's not. But wait a minute. Is there a minus cosine square y on the right hand side? Can you have a y term on the right hand side? No, you cannot. So you first, before you do anything, bring it to the left hand side. And so we have sine square y plus cosine square y. Okay, but still, that's nonlinear, man. You cannot have sine square y, and now you got sine square y plus cosine square y also. So come on, forget it. So that's nonlinear. No. What is sine square y plus cosine square y equal to? Dang, man, you tricked me. Yeah, I did. Sine square y plus cosine square, the identity says it's equal to 1. And so this just becomes what you see there. Tangent x, 1 plus 1 on the left hand side, and because it's just a constant, take it to the right hand side or subtract 1 from both sides to get rid of it from the left hand side. This is what you have. Now look at this. Everything is fine and dandy. The right hand side is purely a function of x. D square y dx square, everything is cool. Dy dx, everything is cool. So this is in fact linear, though it looked very non-linear to begin with. It's highly linear. Cool. Now what? So how about this guy? Whoa, please pay attention. 1 minus y squared dx plus x dy equals. What order? Order? I don't see a dy dx or anything, man. Yeah, could we rewrite this as dy dx, solving, subtract x dy, blah, blah, divide both sides by this and all that. Can we rewrite like that? Yeah, of course we can. What order is it now? Highest derivative is dy dx, first derivative. So that's a first order equation. The only question is this linear or non-linear? Whoa, wait a minute. The y square minus, that y square cannot be on the right hand side, Okay, so make sure that you don't have that y square on the right hand side. Can you do that? Yeah. Split that fraction y square minus 1 over x into y square over x minus 1 over x. And subtract a y square over x on both sides. And so this is what you end up with. Right? If you're not convinced, just do that algebraic manipulation yourself to convince yourself. And that's what it becomes. Now, is that linear or non-linear? Oh, that's non-linear, man. I got it. Because like y square, like you cannot have y square. Yeah, wonderful. You're right. You cannot have y square. And so this is certainly non-linear because of that y square. And so first order, and what did I say? What's with that qualifier in y? Non-linear in y. What do you mean non-linear in y? So is there something like non-linear in y, non-linear in x? Yes, there is. The idea is, in the differential equation is given in terms of differentials like that. Who said you have to form the ratio dy dx? You could make dx dy. Maybe x is the dependent variable and y is the independent variable. Is anything wrong with that? No, nothing wrong with that. Which one we call y equals f of x or x equals f of y? How we choose, it's up to us. That choice is entirely arbitrary. So, before you move on, you better sit down and think about this and rewrite this in terms of dx dy. Okay, similar manipulation, do that and write like this. Now let's examine. Is anything wrong with dx dy? Nope, that's a derivative raised to the power of 1. Is x the dependent variable x? Is that okay? Yeah, that's okay because x raised to the power of 1. Oh, what should its coefficient be? Oh, its coefficient should be purely a function of the independent variable, which happens to be y here. Is the coefficient of x purely a function of y? Yep, 1 over 1 minus y squared is purely a function of y. On the right hand side, we should have a function of the independent variable y. Is 0 a function of y? Yes, it is. Uh-oh. This is actually linear in x. Even though it is nonlinear in y, it is linear in x. So it turns out, given a problem like this, it would be much easier to solve it if you were to express it this way. And in fact, we will learn how to solve differential equations, and we are quite likely to bump into this problem. Right? And by arranging it this way, we can easily solve the problem. However, left in that nonlinear in y way, you cannot. All right, folks? That's it.